So a friend of mine asked me when she heard that I was giving this talk, she said, do you guys present like Sheldon? And I said, no, we try not to. Actually, I gave a presentation here 5 years ago in this very room, and a lot of the slides are very similar because I'm interested in the big question. So apologies to people who saw that, George, Ashish. The one big difference is I've taken out all my slides on deep learning because we're all experts on deep learning now. Anyway, so there's this remarkable thing. We're 100 years and about a month anniversary of Einstein's relativity being kind of first conclusive proof, the bending of light. I love this newspaper headlines. Men of science more or less agog over results. Stars are not where they seem to be, but nobody need worry, you know. Sensationalism isn't that new. One of the cool things about this, of course, is that this is what led people to say tensors are relevant to the real world. And I realized that if you look at tensors, there's this transient, well, there's this very steady state, I guess, with the period of grad schools, people doing their first course in general relativity, and then, of course, this massive increase of tensor flow. And that kind of is a nice kind of metaphor for this meeting. We're bringing together computer science, tensor flow, with traditional astronomy and astrophysics tensors. I noticed there's this little spike in Google Trends. I'm curious as to what TensorFlow was in 2004. I'm not sure whether so now every computer scientist knows about tensors, although I think they think of them as just multi-dimensional arrays. And on that, I found this quote by Einstein. He says, I think it was to Levi Civita. He was saying, "It must be nice to ride through these fields upon the horse of true mathematics, while the like of us have to make our way laboriously on foot." So, that's a nice quote on, tensors were difficult even then. So a little bit. So I'm head of data science at SKA Africa, and this is a kind of artist impression of what the Northern Cape will look like. Thousands, potentially more than that, of dishes. And if you do a back-of-the-envelope calculation of what the kind of data rate could be, if you just said, give me everything, I got something like 10 to 27 bytes per year, which is kind of cool because there's not even a term on Wikipedia for this amount. It goes exap, yotta, whatever. They don't even have a 10 to the 27. So obviously we have to downsample and throw away most of the data. That's the SKA phase 2. What we currently have is Meerkat 64 dishes delivering a couple of terabytes of data per day. We have 25 odd petabytes of storage currently and doing some nice science already. This is a Meerkat image of the center of the Milky Way. You can see these beautiful supernova remnants and stuff like that. So I'm going to focus on what I think are some really important things. Kai has already made a lot of the points, Peter. Several of these points have been made. But I think one of the very interesting things is what I call machine learning against infinity, which is that we are not interested, in many branches of machine learning, we're interested in being as good as human. We're trying to develop AGI, artificial general intelligence. Can we be as good as human? In science, we don't care about humans, right? Almost literally in many cases. We are not trying to be as good as a human astronomer. We're trying to drive systematic errors to zero. And that's actually something that I think machine learning is not currently very well set up to do. So some examples, there was a recent AAAS kind of stir, machine learning causing crisis in science. Machine learning techniques used by thousands of scientists, that's a lot of scientists, are producing results that are misleading and often completely wrong. And I think this goes to the point I made yesterday, that I really think we need to be very dedicated to the scientific principle. And I love this quote by Jacob Bronowski: "The most remarkable discovery ever made by scientists was science itself." So I think maybe there's a room to be curious and more aficionados about the actual scientific method. So here's another example of that machine learning against infinity. This is some Meerkat data, and you can see that there's a lot of RFI, radio frequency interference, which is a huge issue for us. And you can see it. It's like all this stuff is junk, right, that we want to cut out. And so one way you can do it is you say, oh, let's train a machine learning algorithm to detect RFI. Very sensible thing. Well, what's your training data going to be? Well, you could lock 100 radio astronomers in a room. That might be a good start. And force them to draw boxes around the RFI. But of course, what's going to happen? That's a rhetorical question. They're not going to agree, right? The obvious RFI they're going to agree on, but the subtle stuff, they're going to be like, well, is this RFI? Where's the edge of the RFI? So of course, our data that we put in is contaminated because humans are imperfect. How do we deal with that? So analogy is, imagine if you look at this image and I ask you to label all the pixels that are grass. So some of it's obvious, but like some of it's much less obvious. Like, okay, these are weeds, but are weeds grass? And where exactly does it make a transition from grass to weeds? So I think this is actually a really serious issue, because we all know that if you train, your training data controls the quality of your outputs. And my favorite example of this, apologies to those of you who've seen it before, I show it all the time. This is statistical analysis of Israeli High Court parole hearings. On the y-axis is the parole probability, on the x-axis is something, and you can see that the probability varies from 80% to 0. So these are all judges with at least 10 years of experience and like 1,000 parole cases. And so the question is, for those of you who've never seen this before, what do you think is on the x-axis? This really important thing that clearly determines the output. No guesses? You do know, George, because it's time of day. And these dotted lines are food, sugar injections, right? So if you're the last person before lunch, you're not getting out of jail. Sorry, doesn't matter that you saved 1,000 orphans while you were in jail, whatever. And if you're the first person after, well, you're back up to 75%. So even when you ask a human, and I have experienced this, having labeled many, many Sloan supernova images, if you ask the same person to flag RFI just after dinner or at midnight, you'll get completely different RFI flaggings. At midnight, they may just say the whole image is RFI. So this is an interesting new systematic. Then there's the lack of training data. What happens if we only have a very limited training data? Well, one approach is to simulate it. So here's a generative adversarial simulation on FR1 and FR2 type radio galaxies. One column is real, one is fake. So for those of you who haven't seen it, which one is the real? A or B? A or B? It's like the optometrist test. So who thinks that A is the real one? Okay. Who thinks that B is the real one? So by a small majority, we've got B. Usually B wins by a landslide, and it's actually A that is the right column. So this is really interesting. We fool all astronomers, and yet it's so by that definition, if you say that it's good enough if it can fool an astronomer, you might say, well, we can start using these to generate large numbers of training data. But in fact, when we added a lot of generative adversarial models into the training data, it made no improvement on the performance. So that raises the question is, well, how do we know our simulations are good enough? So that sort of goes back to now a new aspect of the scientific method, right? I go and I make simulations and I want to train on them. How do I know if they're good enough? And I don't have answers, so I'm hoping to have good conversations about it. So just to summarize this part, if we train on human-labeled data, inevitably the data will be contaminated, and that contamination will introduce a systematic error. If we try instead to simulate the data, the simulations are never perfect, and we never know if we're missing something important. So we need to think of new diagnostics in a way to figure out if that is the case. Then, of course, on the same theme of machine learning limitations, we know, I'm sure we're all very familiar with the adversarial attacks. So you take this in Google, I think this was a Google classification algorithm, it classifies the image perfectly. You make some small changes, and it now says, oh no, sorry, I made a mistake, it's not a weapon, it's a helicopter, right? So one way to interpret this is that these numbers are not probabilities, right? They're just scores, but they're not rigorous probabilities, and of course we want to do rigorous science, so we need probabilities. So for example, if I asked you to draw a classification boundary from this, you would be able to do it probably in 10 different ways, SVM, k-nearest neighbors, whatever you want. But what about this? Can you draw me a classification boundary now that I've got error bars? Or even worse, what if the red and the blue points are my training data and the black point is my test data? And you can see my black point has got asymmetric error bars. Well, as soon as you do this, the concept of a decision boundary doesn't make any sense, right? Because now you've got a probability distribution. So there's no unique decision boundary. So how do we deal with this? Because this is, of course, what we should be dealing with. We should have errors, and we want those errors. So similarly, anomaly detection, outlier detection. Obviously, it's very easy to see the outlier. There's even an arrow pointing to it. But what about if that object has very large error bars? Now you would say, oh, actually, I'm not sure if that's an anomaly. Or ironically, even if the position of the point is not really anomalous, the size of the error bars is very anomalous. So how do you do anomaly detection when all your points have got errors? So I think this is very important for taking these, taking machine learning into complex pipelines where you need to be able to propagate your errors all the way through the pipeline. And of course, if you do everything in a Bayesian way, you can do that, but currently in machine learning, that's much more challenging. So there's a simple solution, I think, although whenever someone writes simple, it's almost always a lie. It's never simple. So you can actually deal and extend standard algorithms by marginalizing over the unknown true value of the points. And so I think that's an interesting thing to consider. So we developed a specific formulas with my student and Michelle Lochner, but it's definitely not simple, and it comes at a computational cost. So as always, there's a trade-off between quick and dirty and easy versus hard and computationally intensive. And I think this is really important because we don't need to pretend that we used to do science brilliantly and now we're doing machine learning and there's suddenly a crisis, right? If we look at this, John Hooker put together this beautiful plot of the measured value of Hubble constant versus time, you can see it's a human thing to underestimate error bars, right? Essentially, there are only a couple. In all of these, there's probably only 2 data points up until 1970 that had accurate error bar estimates. So doing this properly, propagating errors, is critical in this new era of precision astronomy. If we zoom in on this, we come down to this kind of plot. And of course, now we are here where we have like a modern version of the 50 versus 100 debate, except now it's 67 versus 74. So going back to SKA, how should we do science with the SKA? We've got these thousands of dishes. One way to do it is to do it properly and to say we're going to forward model everything. That means we treat each dish, its deformations, and its pointing. So one of the problems that we have in radio astronomy is that the dishes, you don't know if you're exactly pointing where you think you're pointing. So you might actually be slightly pointing off. So you can imagine, if you look at a bright source and then turn your head, it'll appear slightly dimmer because of the PSF of your eye. So if you try and estimate the brightness of a source, you'll get the wrong answer. And so here's an example. Here's the true sky on the left, the recovered sky, if you don't know that you're pointing slightly off, and the difference is you get very wrong results. So how can you do this? One way is to do a Bayesian forward model that allows for systematic pointing errors, dish deformations, etc. And then what you get is something like this. It's a giant covariance matrix between the things that you care about, in this case the fluxes of the sources, the shape of the beam, and the pointing errors. And so you can see these things correlate together, understandably, right? And then you can just marginalize over the pointing errors. The problem with this is that for SKA, we might end up in 100,000 to 1 million dimensions. So how do we do MCMC in 1 million dimensions? So to summarize this part of the talk, I would say, we want to have full control of our errors so we can propagate them through the pipeline. Currently in cosmology, for example, we do this with MCMC. So then the question is, well, how do we be rigorous with machine learning? And/or how do we sample? Wow, it's wet. How do we sample in very high dimensions? And so density networks potentially, it's well known that sampling in high dimensions is very hard because of the curse of dimensionality. So is there somewhere that is sort of rigorous but computationally efficient? So I think those are very interesting questions. I'll just say a little bit, I must be running out of time fairly soon, about anomaly detection. Obviously, with SKA, we're talking about an exabyte of data a day. The chance of discovering new classes of objects is fantastic, right? But of course, traditionally, we would use human ability to go, that's strange, that's interesting, to identify outliers. But with an exabyte of data, we're not going to be able to do it. We're going to have to use algorithms. And the problem is, of course, is the no free lunch theorem. No anomaly detection algorithm is better than random if you consider the class of all possible anomalies. Another way to say that is you pick your poison of what type of anomaly you think is going to come out, and then you can design an algorithm to detect that, but it will be equally blind to many other anomalies. So here's an example. I was going to show you a nice video, but I can't, unfortunately. So I think we'd all freak out if one of these walked in the door, but if your features that you were using were the number of legs and the number of eyes, then your algorithm would say, no, that's not anomalous, that's fine. So knowing what features you should be looking at such that the object will appear anomalous, of course, is impossible because you don't know what the object is, right? So I think there's an interesting question is, if we limit ourselves not to the space of all possible functions, which is clearly a huge space, but to the subspace of astronomically, physically realizable objects, are there optimal anomaly detection algorithms? So I think that's a very interesting question. And then, of course, with Meerkat, through the Breakthrough Listen, we have the SETI program that's starting, and SKA will, of course, be amazing for looking for extraterrestrial intelligence. But it's a very interesting question. What sorts of signals should we be looking for? How would aliens, if they were trying to communicate with us, what would their likely signals be? And so what kind of detection algorithms should we be using? And I really don't have any good ideas, but I think it's an interesting question. And I think I'll stop there.